analogous systems. So if you had look at the syllabus, uh, I have removed numericals from this part of the subject. So earlier we used to solve some numericals on your analogous system. So this analogous system is just a relationship between how electrical and mechanical systems can be compared. That's it. So there is no huge concept lying behind this. It's just comparing our differential equations and making a conclusion about the elements of the mechanical as well as electrical systems. So there won't be any numericals asked on this topic. But what is the meaning of this? If you understand, that's sufficient. So there are two types. Uh, there are two types of analogous systems. One is force voltage, or we call it as FV, and FV analogous system. And the second one is current, force current, or FI. We call it as FI analogous systems. Fine. So let us see briefly what is force voltage analogous system. So it is just mapping force as a voltage. Mapping force as a voltage, we call it as FV analogous system. So let us consider one mechanical system. Again, the simplest one, MBK, mass, spring, and damper, with a force applied, with a force F of t applied as shown. And obviously, there is only one output variable, which is the linear displacement. Linear displacement, x of t. So the differential equation which governs the dynamics of the system is already known. It's very simple. So let us make one small modification in this equation by considering dx by dt, which is velocity, rate of change of displacement as velocity. So substitute that back in the first equation, we get m dv by dt plus b into v of t plus k. So now this k has x. Okay, how do you get x from v? So v of t is dx by dt. If you want x of t, you just integrate it. You just have to integrate it. So that is k integration of v dt. This is simple mathematics. Okay, I'm just replacing the elements. No concepts hidden here. Okay, so let us call this as expression 1. Then we have consider series RLC circuit. Let me call the source voltage as E of t and the current flowing as I of t. Okay, series RLC circuit, and let me apply the Kirchhoff's voltage law straight away, and it is E of t equals to what is Kirchhoff's voltage law? It's very simple. Okay, try to recall it. I will note down all the voltage drop across each element. So that will be LdI by dt plus R I of t and integration of I of t whole divided by C. So it's very simple. I hope no explanation is needed to write this KVL equation. It's already been done in basic electrical as well as in network theory. So if you compare these two mechanical and electrical equations, they look similar. Okay, they're not same. We call it as specifically analogous, similar. So compare element by element. F of t in mechanical equation is equivalent to voltage E of t in the electrical circuit. So that's why we call this as force voltage analogous systems or FV analogous systems. So F of t here is same as E of t. Let us compare other elements. So velocity in mechanical equation is current in electrical equation is m dv by dt here, L di by dt here. Then let us see the system constants. M is equivalent to L, so we write M is equivalent to L. Then similarly, B is equivalent to R. And the last one is K is equivalent to, is it C or 1 by C? K is
1 by 7.
equivalent to 1 by C. Very simple. So the question may be asked like, write a note on EFV analogous systems or find the relation between mechanical and electrical parameters in a force voltage analogous system. So it is very simple. Just draw one mass spring damper circuit system and then RLC circuit, and then you just need to mark the variables, then apply KVL for force voltage case. So this is FV. So let us look at the second case, a second type of analogous system, which is force current analogous system. So let us consider the same MVK system as the previous one. Same expression, whatever we did. But now for force current, we'll consider a parallel RLC circuit instead of a series RLC circuit. So as I said earlier, nothing much is there to think about this thing. Why parallel, why not series and all. Don't keep all those questions in mind. It's just comparing the equations and relating the parameters. So this is how I will draw parallel RLC, and I will mark the input source for this circuit as I of t because I'm doing for force equivalent to current. So I'll mark the input as current source I of t and let E of t be the node voltage as shown in the diagram. So now I need to write the equation for this particular circuit and I need to apply KCL, as simple as that. Earlier it was KVL, now it is KCL. So everyone is aware about KCL. So the supply current I of t gets divided into all these three elements. Okay. So you can say I of t equal to current through IR, IL and IC. So let us see how the equations can be written. So I'll mark this as IR, and IR is nothing but this voltage divided by the resistance. Simplest Ohm's law, and the same concept can be applied to the remaining elements. So let us see how IC can be written. It is C into dE by dt. And the last one is current through the inductor, IL. So it is equal to 1 by L integration of E dt. So IR, IL and IC are done. So the main current I of t is summation of IR plus IC plus IL. Now compare these two equations and they look similar. Okay, so this is force current analogous case. So now compare element by element of both the equations. Suppose is equivalent to current. Then what about velocity is equivalent to? It is equal to the voltage, the node voltage E of t. Now carefully compare the elements. Okay, so dV by dt and dE by dt. So they are similar equations. So M is equivalent to C. Then B is equivalent to 1 by R, not R. Okay, equivalent to 1 by R. It's not just R. Then K is equivalent to 1 by L. So this is the force current analogy, analogous circuits. So the only reason I removed this from the, numericals are removed from this particular topic. The reason is that these numericals neither appeared in any competitive exam or it wasn't asked in any interview, but you should have the knowledge. It will be helpful in some or the other way. So you just should know that there exists something called analogous systems. Is that sufficient? information. So though there is no numerical, I would like to show just two numericals which are out of this scope of our syllabus. So nothing to get panic that this numerical won't be asked definitely. So to reduce the discussion time, I have directly taken from one of the textbook. Okay, I have directly taken it from one of the textbook. So this is the question. It is asked to find the force voltage analogous of this system. Okay, force voltage analogous of this system. Let's glance the numerical. We have mass spring and damper blocks. Just to create a confusion, they have drawn M2 inside M1 and there exists a friction between M1 and M2, which is V2. So just for the sake of understanding, you can assume this M1 as one single block like this and K2 and B2 exist parallel to this between M1 and M2. So that's it. I repeat, just to make a confusion, they have drawn one mass inside the other and represented friction between those two as V2. So to simplify, we will consider M1 like this and M2 as it is, and one K spring K2 like this, and another B2 we will draw parallel to this. So those who want can note down this diagram. It will be helpful in finding the transfer function. Okay, but we will not be solving it right now. I will give this as a practice numerical and I will give its solution also later. So as of now, just think this diagram and how to convert this to force voltage equivalent diagram. So force voltage equivalent diagram. So we already know the relation between F, okay, force, then X, then MBK in force voltage scenario. So directly we will draw the equivalent diagram. So in the equivalent diagram, there is one displacement with respect to M1, another displacement with respect to X2. Then K2 and B2 are common to M1 and M2. Then K1 and B1 are connected to one rigid body and the other end to M1. So without any doubt, f of t equal to x1. So at x1 we have M1, K1, B1, and at x2 we have M2, and between x1 and x2 we have K2 and B2. Okay, so don't ask me how we get this, because I have already told. We will move a little fast. Then we have the equations at two different nodes, at node x1 and at node x2. So at node x1, let us see m1 d square x1 by dt square plus k1 x1 plus b1 dx1 by dt. So these are all now familiar. Then k2 x1 minus x2 because it is with respect to node 1. Then b2 d by dt x1 minus x2, which is equal to balanced by the applied force f of t. So after writing the nodal equation, since we have two output parameters x1 and x2, now we will be getting two velocities as v1 equals to dx1 by dt, v2 equal to dx2 by dt. So this replacement is must. This replacement is must. So when you replace, we will get this particular equation with v1 and v2. Okay, you can try it. I will share it anyhow. You can try it later if you want, but I will make it clear again. No numerical will be asked. Next at x2, node x2, we have written the equation. So we have m2 d square x2 by dt square. Then k2 and v2 are common elements. So this comes as x2 minus x1 for the relative displacement. Again, replacing the velocity terms, we get the second nodal equation of this particular type. So now we take the mechanical equations at both the nodes. Then we compare that with the force voltage analogy. The force voltage analogy, we already know that F is replaced by voltage E of t, and the velocity is replaced by I of t, and M is replaced by L, B is by R, the resistance, and K replaced by the 1 by C element. Okay, so this particular, just hold on. ಇಲ್ಲ ಕ್ಲಾಸ್ ನಡೆದಿದೆ ಅಂತ ಹೇಳೋದು 12:15ವರೆಗೂ ನಾನು ಆಮೇಲೆ ಕೊಡ್ತೀನಿ. ಸಾರಿ ಫಾರ್ Sorry for the interruption. Then upon replacing all these elements, M is replaced by L, so M1 goes as L1. Similarly, B1 goes as R1 and B2 goes as R2. So like K1 goes as 1 by C1 and K2 is 1 by C2. So replace all these elements, you will get electrical equation. So you get one electrical equation, and this equation will tell you how the force voltage analogy can be used to draw the electrical circuit. So you can see now L1 is independent, C1 is independent, R1 is independent, whereas C2 is common to other loop where current I2 is flowing, and R2 is a common element with the other loop where I2 is flowing. So only C2 and R2 are common to some other loop. Rest all L1, C1 and R1 are independent. They are present in only the first loop, you can say, where only I1 is flowing. So first draw only this part. Okay, draw L1, C1 and represent R1. Then make sure that C2 and R2 is common, therefore they can be placed at the right side of the circuit. So now look at the second equation, and you can make an easy conclusion again that R2 and C2 are common to some other loop, okay, which is the first loop now. Okay, so they will be kept as it is, whereas L2, which is independent to only for the second loop, will be drawn here. Okay, so that's it. So draw this circuit, represent I1, I2, then input E of t, and write whichever element is coming at this position, L1, C1 and all. Okay, so it's very simple, it's not difficult. So for the sake of knowledge, you should better refer it once and if possible, solve this. There's one scenario. So this analogy was done for translation system. Okay, and there isn't a much difference for rotational system. Okay, there is not much difference between translation and rotation system. We already know that in rotational case we have T of t instead of F of t. Okay, so this particular numerical is for force current analogy I have chosen. So in this scenario we have T of t in the place of F of t, and velocity now will be angular velocity. So velocity v of t, the linear velocity will get replaced by angular velocity omega of t. So force current now becomes torque current analogy. Torque current analogy. So J goes with M is replaced by J. So J is C here. Then B is 1 by R. K is 1 by L. You can compare directly with our previous derivation. Fine. So that's it. First write the equivalent diagram. Then write the corresponding equation, differential equations at each node, and replace angular velocities as shown in this equation. So once you replace with angular velocities, you will have this final equation. In this final equation for torque current, what all elements should be replaced. So you replace those elements and keep the final electric equation for node 1. Then the second node equation, mechanical equation goes like this. Then replace it by angular velocity. Then compare this table with this equation and replace all the elements. So once you compare both the electric equations, you can say 1.27 and 1.28, you can make out the conclusion easily again. R1 and C1 are independent, whereas L1 is common between two nodes. Similarly, C2, R2, L2 are independent with respect to second node, and then you will have L1 which is common to this node, second, between second and first node. So that's it. There won't be any derivation of transfer function. And you just need to understand how the analogous system can be written. So I hope the concepts for this are clear about analogous systems. So just understand one numerical, that will be sufficient. So in the next class, we will go ahead with a block diagram. What is block diagram and understanding of it? What is the necessity? And after that, we will be doing a signal flow graph concept. Fine. So that's it for today's class, and really sorry for the delay in starting the class. So this is how the future classes will go, like at the same speed. So try to catch up the things as early as possible. Okay, fine. Thank you. Thank you, one and all.
Thank you, sir.